Welcome to Rudy's Electronics Lab, to the second episode. We're going to talk about the Fireberd 6000A pattern generator and analyzers. I already did an earlier episode where I talked about all the basics of the device, where we looked at all the options, all the different interface boards, where we looked at the block diagram and principles, everything. And in this second episode, actually, we're going to do hands-on measurements on the device, quite a couple of different ones actually. And finally, we're going to talk about whether it's worth considering this device as a general purpose instrument in the 2020s. Hope you're going to enjoy it. So I made a little test setup here with also an oscilloscope so we can see the generated and received signals, and another BER analyzer. And yeah, so here we got our Fireberd. Let's fire it up. Just powered it. All the lights will light except the SP. So SP is space and M key is mark. That is quite useful basically to do. Software version T, that's the latest software version. I didn't get any errors. If I boot it up after a couple of days, I would get an error that the time is not set and the date is not set. That's because the backup battery is empty in this unit. But I'm not really sure I even want to take the trouble of repairing it, because the manual explains that it only basically stores things like the time and the date and that type of parameters, and not any relevant test settings or calibration settings. So I don't care about that too much. So basically here we got the device, and let's take a look at the user interface. On the left it's mostly related here to the generator part, and here we see the feedback on the analyzer part and the analyzer result here, although some of the settings will relate to both. So we'll simply generate now some signals and loop them right back into the device, so we can then have the analyzer show back what types of signals were received. And I'll be using the LAB interface now. I'll get later into more details there, but that allows me to easily hook up other devices, at least another BER generator. I'll do that in a moment. But anyway, this is the kind of setup here. We basically can go through a variety of different menus here. So here we would have the interface menu, and I would could select like the internal serial interface, or I could basically go one step back and have the LAB interface, which is the interface that I got right now. I can set here a variety of different bit patterns that are being sent here, and I'll do a NP15 type of thing. So that's 2 to the power of 15 minus 1 bits cycle before it gets back. Earlier tests I've been doing with MP9, so that's 2 to the power of 9 minus 1, so that's 512 minus 1 is 511. We'll be setting here the internal synthesizer, and it's now set on 1000 kilohertz. That's 1 megahertz. Oh, that's quite okay. So I'll leave it at that in a moment. And I basically got my loopback already working, because I can see mark and space are both being received. Actually, if I would go to mark here, sorry, one to mark. Yeah, I would only see marks, but there are no spaces. So there's only ones and no zeros being received. And if I go here to the signal I want to analyze, I see the mark and the space, and I see a sync signal being detected. And I looped both the clock and the data signal back into the unit. With most units you can actually use the self loop for that, but the LAB interface is actually the only interface card that I have that does not support the self loop. It's too bad that he doesn't tell that on the display. So I made a physical loopback, which is perfectly fine as well. And actually already went right away into test mode. I'm internally generating my frequency that I just set. I can also have a frequency as a BSC input on the interface, and a BSC input on the device itself, and is running in sync mode. And all of these interfaces here, basically, there are a lot of sub-menus under it. So let me just show you how that works. If I go to the auxiliary menu, I can go to a list, and I can go through you know, many different items here. I can go up. It's a little bit getting used to it, how it works, but actually I do like the interface quite a lot, what I've been able to do in this simple but very straightforward type of interface. And yeah, we get to the analysis reporting in a moment. No, let's do it right now. So the analyzer screen, we can see we got a frequency coming in at 1 megahertz here. So that's indeed also the send frequency. So the loop is properly working. And I have not observed any bit errors yet. He's already into testing now. Now, how can we see that the unit is working properly? By creating errors ourselves. So just press this button here. And you might hear I'm getting a beep. So every time I'm pressing the button, one single bit error has been generated, inserted into the signal, and the receiver indeed picks that up nicely. Now we can also go and see these signals on the oscilloscope right over here, because the nice thing is that the unit has a lot of pins on the backside, test pins, we could call them, or whatever pins, where you can follow the signal. So here I got the data signal. As you can see, it indeed looks a bit like a pseudo-random or a random type of signal, and the data signal. But there are many more test pins basically. So I actually connected a whole set of test pins here to the logic analyzer. Let's turn it on. And we got a whole bunch of test pins here coming into the system. So let's explore them a little bit more, what we got here. Can make them a little bit bigger. We got the receiver data signal, the receiver clock signal, so basically kind of similar to above. We got the generator clock signal and the generator data signal. They are now identical because I've just looped them back into the device, but if you do some real testing, they might of course not be identical, or with external sources, etc. We also got, and I write that a lot, a sync generator. So that indicates the start of the pseudo-random sequence, and we both got that on the receiver side and on the generator side, and you will see that the receiver side will lag a little bit in time before it actually regenerated that type of signal. And we also got an error signal, and when I just press the arrow button, we might or might not have seen an error coming by here, but then again we're sending over millions of bits, and the scope, because of blind time, you know, will not show everything. But in a moment I will show you more of that. And we also got a signal here that the device is actually in sync status right here. So we basically see like all the kind of important data coming in. Now let me now try to see if we generate a little bit more errors, and once I use again the error insert button, but I keep it pressed, it will continue to insert errors at a kind of a predefined rate. So let's do that. I'm getting a lot of beeping, I'm getting a lot of bit errors right over here. I'm in the menu that is showing me bit errors. And now if we look on the oscilloscope, yeah, once in a while we do basically see errors coming in here. We do see differences between the send and the receive signal, data signal, and we see the error bit basically coming in here. So paying a little bit attention here to this analysis section, we basically got two different measurement shows. And each of them can be set as you wish. So you can even set them to the same thing. So now I both set them to bit errors. That doesn't make a great deal of sense. But in the category of bit errors, I can, for example, go to average bit error. And so the average bit error that's being introduced here, let's do a restart. Because there was also a time when I had no errors. So actually he's inserting one error in every 1000 bits being sent, as I see here in the error rate. And if I stop including errors, then the average error rate will go down. You can also show the spontaneous error rate at this right very moment instead of average. There's a lot of settings. Actually, it is quite amazing how many settings there are here. And I also created this little sheet just to give you an overview of all the different measurement settings that you can get on the device under this simple set of menus here. It depends really on the interface as well. So certainly not every interface will have all of these settings kind of at the same time. But it really has a very advanced type of, or well thought through type of interface in order to show errors on the device. Now, if showing just two different measurement values is not enough for you, there is a nice little trick, because actually the units support extensive use of a external printer, which is connected via a serial interface, and the printer can be connected to have an event type of output, so you can do all type of triggers and alarm settings, and then it would print it out. You would find it next days. It can create kind of tables where you see like every hour or so the average of certain measurement parameters. But it can also like output all the measurement parameter at once or a selection of them. And I don't have any serial printers still hanging around, lying around in the house. But I hooked it up to a computer with a RS-232 to USB converter and used the computer terminal program for them. And actually I will be showing you here, actually I'm playing it back slightly faster than the device is outputting it, how you can see not only two but all the measured output parameters at one single time. And you can also show all the settings of the device at one output. Now, of course, I'm kind of interested to see as well how this device works if I actually combine it with other devices here. So what I have been doing here, basically, I've been first connecting it to an external BER analyzer. So I'm using this one as a generator now. I'm feeding the signal that I'm looping back actually at the same time into the Anritsu, and I'm interested to see what type of errors that I am getting here. So let's see if we can configure the Anritsu in the right way here. I've done other videos on the Anritsu itself, but and even some that look more into the bit error analysis type of thing. So I'll just quickly try to see if I get everything to the right setting. I have to get into the utility menu. I have to get into the BER test menu, and I basically have here, I think, most of the correct settings. I don't need resyncing, I think, continuous mode. Data type is PN15. That's important. You don't need to know the speed because there's a clock coming in, so he will get it from that. But we do need to set it at the right type of sequence. So that is set to PN15. So this has to be set on PN15 as well. And the count mode is just telling us how many bits he will evaluate before reporting the results. So I think everything is properly set. I hope so. And yeah, there's also some polarity and rise and fall. I guess it's all fine. So let's just start testing. Oh, we're good. And we're getting an error rate of 0 errors. It's always being shown as a scientific notation type of thing here. And right now we're not introducing any errors, so that kind of should make sense. If I insert some single errors, yeah, I see 1 to 10 minus 6, and now it disappears again. So these are single errors. And once I go to a continuous error insert, yeah, I get to 1 to 10 minus 3 errors, so 1 error out of every 1000 bits. And exactly that is the same error rate that I got on measuring the device by itself. I should restart it here again to make sure I get the same averages here. Yeah, but it basically means all is fine, and it's measuring like, or it's sending the rate that can actually be measured by the Anritsu in the same way as one would expect it to be. Those that have been following other episodes of my channel know that I put quite a bit of effort into building my own pseudo-random bit generator, a PN9 generator. Motivated by the fact that there are very few, at least new devices, affordable devices that can do this type of thing. An interesting exception, by the way, is the new Siglent SDG 1000X Plus series, I believe, that is just introduced a update of a device which has an added PN generator in it. I will be having one soon in the lab, I expect, so I'll be reviewing that obviously. But of course I'm super excited to see whether the Fireberd actually properly receives the signal from my homebrew type of generator. So I connected it up. I basically configured the device to the code length, which is PN9, so 512 minus 1 is 511. And I've also been setting up the Anritsu at the same time, so he's measuring the same signal here. And right now we're seeing 0 errors. We are being synced. We see 1s and 0s, and there's simply 0 errors coming in of the device, and he's noting a frequency of 100 kilohertz, which is correct. That's the internal default frequency of the device. So let's introduce some errors. 0.049 BER. And yes, that's what I'm getting here. 4.9 to the 10 minus 4, 4.9 10 of minus 4. So yes, we got the same type of measurements here. One error every single sequence, so 0.196 BER rate, 0.196 BER rate, 0.196 BER rate. Yeah, so it does exactly the same job here as the Anritzo. However, this can play a special trick that the Anritzo is not able to, and I'm pretty excited about that. Because now we're feeding the devices both by data and clock signals, and that is what most BER testers expect. And if I disconnect the clock signal, then both of them basically don't work anymore. My Anritzo stopped, and my Fireberd basically says no clock, and the light sync lost is burning, and even if I press it, there's going to be no resyncing going on. The receive frequency went 1 to 0. Now, what is a special trick that the Fireberd can do? It got a clock recovery mode. So if I go to recovery here, he's recovering back the 100K frequency from the incoming data signal, and indeed we're seeing the right error rate again. And if I go introduce more errors, 294, yeah, 294, 0.391, 391, perfect. Yeah, so we see that it actually perfectly picks up all the signal generated by my own device, even when the clock is missing. And why I'm kind of excited about that, because that would also allow me to do some testing when I do wireless connections via via all types of Arduino type of setups with signals, with LAN type of signals, whatever I want to play with, because then often I don't have a clock anymore after getting it from a mobile unit, and the recovery possibility here, that is really something that I very much value. So that is a big plus over some of the existing, and I think most of the BER testers that are down on the market. It can work without a clock signal. There is one nice feature of the outputs of the lab interface that I would like to show you, and that is a button on the back side, and I've connected it to my oscilloscope. I took the data out pin there, and look at the kind of unusual connection I made at my scope. As you'll see, I'm not bringing in the BNC directly into the scope, but I'm bringing the one channel into the one side into the one channel and the other side into the other channel. Because mind you, if we look well at the connector on the lab interface, we will see that this is not a symmetrical of the that is not a grounded BNC, it is a floating BNC with respect to the frame. And in a moment we will see why this is the case. So this is the regular type of output that you would getting from here. I'm syncing it here a couple of times, and the center pin basically would have a 5-volt TTL-like type of signal, and the shielding would basically have nothing right now in this setting here. And also note that I have a reasonable amount or unreasonable amount of ringing. I deliberately did not put termination resistance of 50 ohms there, so we could see any of such signals there. Now, there is a button on the back side, and when I start to turn that button on the interface, I'm looking for the button right now, yeah, there it is. And I put it to the second step and I'm syncing it. And then you will see that we'll actually get a second signal, which is the opposite of the first signal, the opposite type of polarity. Now, if I go to the third one, I get again one single signal, but it is going to be a stronger signal with both a positive and a negative voltage there. So this is basically a signal going from +5 to -5. So it's going to be a symmetrical signal or a bipolar signal, I think I should say here. And mind you, also we're still getting to see the type of ringing here, even on the connector that is not used. And in the fourth position, we get a combination of both, and both signals are basically bipolar type of signals, and they are opposite. And this opposite allows us to make a balanced type of signal. And this balanced type of signal is great basically to remove any any noise that it picked up on the road. So then normally the receiver basically would have a balanced input and would invert the second input and add it to the first one, and that would kind of cancel out all things. Actually, I did that in the scope right here, creating a mask channel, which exactly does that. It takes channel 1 minus channel 2, and look at that. I get a channel similar in polarity to channel 1, but basically it's a much cleaner signal. So even the ringing kind of gets nicely moved away. So I didn't necessarily expect that the ringing is actually symmetrical, but apparently the ringing down here on the negative side is similar to the ring on the positive side, and this is what I'm getting here. So this is a very nice touch that you have both this balanced type of signals and this bipolar signals, and any of the 4 combinations that you can make there. In case that you're wondering where the magical trigger from the scope comes from, well, that's very easy. I'm using a couple of foot pedals to do that, the ones that you regularly find also in the music field, and I'm just adding a couple of old, almost, well, usually I use depleted batteries or so in series with it, and use it as a sync input for my scope, which is an easy way to trigger signals when I have my hands already occupied or so. So that's a nice touch on the LAB interface. On top of it, the LAB interface because now we're talking about the output ports, obviously, and it can do this with both output ports, data and clock. On the input side, it also has a nice touch in the sense that you can basically set different type of termination values that are common in the telecom industry, including the regular 50 ohm type of termination. And on top of it, you can also decide whether it's sensitive to an upgoing clock signal, a downgoing clock signal, an upgoing data signal, and a downgoing data signal, with a couple of buttons on the back. Again, making this unit quite versatile. Now, since I'm going to dig a little bit more into specific use with telecommunications lines and with trunk lines, I'll be focusing on this episode on the European trunk interface. I could also have done the US trunk interface because I also got the cards for that, but I'm going to try to use the European interface and see a little bit what we can do there. And I want to do a little primer basically to refresh or to inform you about what this interface really is and then how the device can use it. So basically the European E1 standard is a interface for multiplexing up to 32 telephone circuits, which is to be used basically between central offices within a telecommunications network. It does so by creating a 2 megabit or precisely 2.048 megabit per second trunk line, and in that we got these 32 phone circuits that are 64 kilobit per second each. In a typical type of configuration, you don't use 32 phone circuits, but you use 31 or maybe 30 because you might want to use some remaining slots basically for transferring signaling information, but I'll be skipping that part here for my further explanation. Now, so how is this multiplexing taking place? It basically does so by using time frames, and these are short time frames that have just 8 bits per telephone call. So it's short in the sense that it's less than 4 microseconds, and then comes basically the second time slot by the second phone, the third time slot by the third phone, all the way until we had all 32 slots, and then we start in the beginning again. So the capacity for each of the streams basically is 64 kilobits per second, even though I think there's a adaptive mode also for 56, so you can have slightly more capacity there. This might also explain why in the long past, when we still had analog type of telephone modems, at that time you couldn't go above 64 kilobits per second in theory, as long as you were still going over trunk line and if you would not split out that type of modem signal like with ASDL out of your telecom network, which they started to do later on. Now, also one of the nice things is just doing 8 bits per phone call before it goes to the next phone call. So meaning there's a kind of 800 frames per second. The thing that they did that because there is really a minimum time delay, because you're just sending 8 bits and then 8 bits for the next phone, etc. You're already back to your phone for the next 8 bit. There is really a indistinguishable time difference coming in with this type of of type thing. In mobile networks, we often take much longer sets of bits based to send, and that has totally different reasons for time reasons between mobile terminals, but here we don't need to take care of that, so here we can create an interface that is super fast in terms of latency. Now, how does that relate then to these units here? These units have a number of different modes that they support. You can select them from the front panel of the device in the software. And here you see all the different nodes it has, and I'm going to quickly go through them so we understand them a bit better. So the full 2M mode is very simple. It just creates a stream of 2 megabits a second, and it receives it on the other side. And you can do that perfectly in one device. So actually, if you just got one Fireberd and one of these devices, you're going to be fine. Actually, for almost all the tests that I'm doing, you could also do it with one single device, but I find it kind of interesting and to be able to separate these things. Then we got a mode in which we can have multiple 64K streams, and you can all select them basically where you're going to set a test code over them, and for which of these time slots you're going to have an idle code over them. And you can select separately in the device what the test codes are, of course, but also what the idle codes are. Then you got the insert mode, and here it gets pretty interesting. So what it does basically is that it has an incoming signal, which might be a real live telephone type of signal, and then you can tell him, I want, for example, a selected number of time slots, like for example number 2 and 29 in my example, and those I want to take the original information out. I want to insert my own test pattern, and then in the receiving type of unit we say I want to just pick out these 2 test patterns again. I want to be able to test those on my analyzer, etc. But the rest of the traffic must still go through. And here you see really how this device can be used in a network setting where you're not interrupting existing traffic. So suppose that you do have this satellite link between 2 parts of the world and you want to monitor that link. And so you might have like some 30 voice calls on that or whatever, etc. And one circuit which is really used by this unit. And this really allows you to insert your information only in that time slot that you want to use for testing without interrupting the regular type of use of your telecommunications line. And in the type of similar vein, you can also do that in the voice mode. And in the voice mode, it actually just takes the signal from the telephone handset. And that's why there were also a couple of handsets with my unit, because you really connect a single handset and pick up signals for it, and the other side kind of take out those signals again using a regular analog type of handset. Then we got a test loopback mode, which kind of loops everything back in the device. There's also a self-loop mode. That is the button on the front of the device with a red light in it. I think it's kind of burning now on my unit. But these are slightly different. The self-loop mode, you don't have externally generated signals. In the TLB mode, I found out you do have these external signals being generated. So it's a bit more useful. And I've connected the both units with a coaxial cable, and that's a 75 ohm cable, because that is how European trunks are being, EE1 trunks are being defined. Now, the unit is currently running. I see the data signal and I also see all the test pins here, but I'm currently still running on the internal RS232 interface. So I'm going to move away from that one. I'm going to choose the European trunk line interface. There's a signal coming in at this internal analyzer of 2 megahertz or 2048 kilohertz, and that is the clock frequency defined for the E1 trunk line. But since we're getting it here, that means we're still in the internal loop, and indeed the self loop is activated, so he's not sending anything there, he's just keeping the signal looped inside. So let me go and send it to the second unit. We got here the signal disappearing, there's no clock, and on the second unit we indeed see now that there is a signal coming in. That unit was already set to the E1 interface. And if I insert an error, and you can also hear the beep, I hope, we see an error coming in over there, and another error. And if I keep this button pressed, a whole truckload of errors, and I could show the bit error rate and other things, etc. So we're basically already seeing that the 2 devices are successful communicating. At least this one is transmitting and this one is receiving. It might also be worthwhile to look a little bit at the type of signal that we're getting, because this is the actual data signal, but so the raw bits within the device. This is actually the signal going over the trunk line, and you can see it's a rather different type of thing. It's a kind of a non-going to zero signal. It has a slightly higher frequency, and somehow the information is hidden in here. So that is the type of signals that are being defined for this type of telecom interface. Let's have it running again. But of course we're interested in this interface because it can do multiple telephone lines. Because what we're seeing now is the raw information of the full 2 megabit interface being sent here. And actually we see that when we go to mode, the mode is full 2M, which is like the full interface. I can also say to send a number of times 64K signals. I can kind of insert one particular signal out of the 32 or so signals, so I can have a particular test signal on one or more on the voice channels, but not on the other channels, and then analyze them on the other side. And this makes this device very powerful because you could use it, for example, while it's actually operating 30 voice connections in a commercial environment. Connection 31 could be a test from the one Fireberd to the other one. But I actually want to do another test here, and for that I go to the More button, and that is the voice part. I will be adding in a voice signal, and I got a unit with a whole load of handsets. Actually the only thing broken in the end of the unit was actually that some of the handsets were broken, so that caused me a lot of problem because that's the last place where I expected that the problem was. And so eventually I ended up testing the thing with another handset that I found lying around. Anyway, we got the unit running here. I defined it that it has to send a signal here at time slot number 4, and I'm interested if the other unit receives that signal. But of course then we should be listening to the signal, so I'm gonna need something additional to do that, and I prepared it right over here, a little loudspeaker. And I'm interested to see if I can send any signal over from the transmitting unit to the receiving unit right over there. Okay, now I'm sending out the full 2M 2 megabit signal, and my unit is working in the sense that this is listening to radio or telephony calls, but it's just hearing random bits coming by. Now let's try to set this unit to voice mode and sending out some signal. And I could use a telephone handset, of course. The problem is that when I'm talking, it gets there exactly at the same time, and you won't hear what my voice is and what the repeated voice is. So I would need a delay or so I thought about an easier thing. I took a little music player here, and I'm going to play a song from here. And I think it's running now. So I'm sending out here a music signal on voice channel 4. This one is set to voice channel 1. So let me go up. 5, 4, there we go. It's very low now. And there we got it going in. So we got one of the 32 channels. We got our little unit here, and we got it playing music. We can send it out on multiple channels. We can do all type of analysis things. And only if we listen to this channel, if we go one channel down, channel 3, there's no noise. I can decide what is there. On number 4 there's the signal, and number 5 there is not. Down again. So this basically demonstrates that there is, that we can actually have like voice communications going over the units. Now, another nice thing to see that we can actually see the time slots when data is being sent over. Because if we look carefully here on the oscilloscope, and we got like one voice channel in, we actually see here that this voice channel is right over here in the data, and actually that is the generator clock. So clock signal is only generated down there, and we can also see kind of in the action of the data that there is music playing right over here. And in some of the other modes we will actually be able to play actually activate multiple of these time slots, I believe. So if we basically go to n times 64K, we already see here that we got 3 different time slots being activated. So on the unit with up and down, we can basically decide here, channel number 2, I could make it a send or a receive signal. So we see an additional channel being added over there. We have to mind the relative sync pulse here. And so basically this way then multiple channels could be added in. I think this is a very high channel, so we're not even getting it into the picture. But we can basically see the different channels that are active at a time and the other channels where no information is being transmitted. Another function well worth to check out is the jitter function. So this unit is actually equipped with an optional board that can both generate and analyze jitter on the interface or on the line. And we can also see what effect that has on bit errors, because if the clock jitter kind of gets out of hand, then at some point we will go and see bit errors there. So let's go and explore that a little bit. So I set up the unit. Is running on the E1 interface. Actually, the jitter card installed in this unit is only compatible with the E1 European trunk interface. And on my other unit, I got a separate jitter generator and jitter analyzer card. But on the other unit, they're only compatible with the American T1 interface. So these cards are specific. This is a single card with both the generator and the analyzer, and the others is two separate cards to be installed in the unit. So now we're basically running an E1 interface with the device itself in its self loop. I see the frequency I'm expecting, that is 2048 kilohertz, so about 2 megahertz here, and the unit is reporting no error. I can insert a manual error and then we get to see a manual error, and I can press restart and then he resets all the analysis findings. So let's go and see for the jitter menu, which becomes available here if you got like the right interface installed and the right cards in here. So basically we got, if we are on the interface here, this is the highest level. We got the generator part. We got a separate analysis part where you can make kind of histograms to an external serial printer. That I don't have. I got something about hit threshold settings, which I'm not going to use in my. I think I'm going to go to the generator. The generator is off right now. So let's turn it to a sine wave. And before I do so, I see that my clock signal here on the oscilloscope is a very tight clock signal. And let me reset my my device statistics. When I'm not sitting right in front of the device, I often misclick. Yeah, so we see exactly that clock frequency we're expecting, and we got a standard deviation of, what is it, 19 hertz on 2 megahertz in total. The clock is not super stable. I mean, this is not a reference Rubium clock or something like that, but we're happy with it, and it's a fairly constant clock here. Now we're going to try to see to add some jitter to the equation. So I'm going to have sine modulation here, and what we can already see right now is that the clock is starting to show some issues right here, and also seeing that in the standard derivation, which already been running into kilohertz right now. So clearly there is significant jitter going on, but apparently we have no bit errors yet. So let's see how much jitter we actually have been adding here. And just before I stopped with this manual, I selected a sine jitter, but I can also have square. I can have ramping. I can have an external input 1. Actually, I just selected it. External input 2. Let's stay with the sine wave. So apart from the type of wave, we have a number of options here in amplification. I'm not going to touch upon that too much. And the frequency. And the frequency is kind of the most important setting. That's the amount of jitter that has been added to the clock signal. So you can either have it sweeping or you can set it in hertz. So actually you see now that it is set at 5 kilohertz of added jitter. And the jitter, as I already noted, is quite visible but not leading yet to bit errors. So now let me play around a little bit and try to find a point where the telecommunication protocol is not tolerant anymore to the amount of jitter that we're adding. So 5 kilohertz, you can start all the way down at 10 hertz, but I know at 5 kilohertz it's still going to work. I'm going to bring it to 6 kilohertz. Protocol is still doing well. I'm going to bring it to 7. It's still good. I can also use the numeric pad here. 8 kilohertz. 9. Ooh, at 9 we're going to see some occasional errors. Not that many, we got 600 errors on the 2 megabit thing, but at 9 we start to see errors. Yeah, and I went to from 10 to 20 kilohertz, and then we actually, it's getting very bad. We're only getting errors, and it even lost the entire sync out of this unit. So let us bring back to 8 and reset the device. Yeah, and at 8 kilohertz of additional jitter, we are still good. At 10 kilohertz, we're going to see the first amounts of jitter here. So this basically allows you to test the tolerance of the protocol to jitter fluctuations, which we see right here. But also could be interesting, I guess, in some occasions if you need to create jitter yourself for your own type of projects. I'll get into the use of this device as a general purpose instrument later on. But you have this ability. But later I'll note also that you also have some. It is rather flexible. There are a lot of different settings in basically creating the type of jitter. But there's also particular types of pretty strong limitations here that I'll get into later on. When measuring issues with signals, such as in their frequency or amplitude, etc., one thing that I really like is using the Siglent SDS2000X Plus oscilloscope and some of the other Siglent models, because you don't have only the statistics, but it's also showing a bar graph with it, and that can be pretty powerful to get some understanding into the distribution of values that you're seeing. So the bar graph can be clicked and it gets bigger, and what you're getting to see then, and I think we can move it to the middle of the screen here, that are little red dots that are kind of indicating what are the last additions basically to the bar graph. But to make a good calculation, I think we should first leave this menu right here and change the time base so we just get like one single signal in here, so it has a better measurement. One thing I'm always missing on this scope that I only have the preset mode for going between horizontal, and I cannot do like 1.5 times to get exactly a single wave form. But that's the way it is. So let's take that one. Let's take a look at the larger diagram. So we see the little red dots here coming. We can make it even a larger one, and I think there's even one more time, and then we get the very largest setting, and we actually get some additional things here, because in the very largest one you can also set a index, which is a manual process with these 2 little buttons over here. And if I set that index to 2048 megahertz, that is the supposed value that we're getting here. Now I've been playing around with it a little bit, so let's clear all the sweeps. I put it on the count level, so we're basically seeing a count now of the number of instances. And what we do seem to see, I believe, if we wait a little bit longer, and we're going to peek a little bit on the left side and a little bit on the right side. Now, mind you, this is with a sine wave as a modulating parameters for. That's the way that the FFT of the Fireberd is being set. So with a square wave, I think it would be kind of jumping between values over there. But this gives us some insight into the way that that is being distributed. This is a function that I really like. It's a function that is missing on my Roden and Schwartz RTB 2000 oscilloscope. But then again, we cannot save the measurement value from the statistics on this device. And that is what we can do indeed with the Roden and Schwartz, so we can do much more advanced analysis. So it's a bit of a miss on the Roden and Schwartz that they don't have this visually on the screen, but the fact that it can save it and then you can later analyze it with computer software is actually a big plus as well. So each of the devices got their strengths and their weaknesses here. I think there are a couple of more parameters that you can set here, but we don't need to get into that right now. One of the other things that the device can do is also create asynchronous type of messages. So that means that it is a message that basically you would have a predefined type of format with a number of data bits, a start and a stop, etc. Like like the regular type of data goes over a serial bus, like RS-232 or UART, as is commonly called on oscilloscopes. And to do this, basically, you set it on the async and you make sure that all the other settings match in terms of the data length, 7, 8, 9 bits. And if we do that, then we actually get to see, yeah, I hope you can see it, Moody's Electronics Lab. So you can have predefined messages that you program into the unit. Actually, you have to do it by entering the hexadecimal values. You have to do it also in 7 bits, by the way. That's the way it is being defined, and you have to set your scope as well to 7 bits in this mode. It can also do 8 bits, but then it uses another alphabet than the ASCII alphabet, which is a bit of interesting or so. But if you want to use the ASCII alphabet that the oscilloscope can decode, then you must use the 7-bit setting here. So there can be a number of predefined messages that you can enter there yourself that represent hex values. You see the issues that we do get some errors here, and it's reported insert on the right of the scope. That merely means that the full frame, that's the error message of the rodent as well, that the full frame is not in the picture. So somehow you need to have exactly the full frame in the single capture in order to get it without this error message of insert, because then there's a disparity between, yeah, it's not fully in the frame, the message. But since the messages that this device sends are so close together, there's no time between them, it's kind of almost impossible to really capture just one single message. I've been playing around a little bit with it. And for those that took a close look already at the front panel, they might have wondering what is this kind of curious fox thingy here is. So let's go there, and then we get to see, yeah, the lazy dog. Yeah, I should get the measure right. The quick brown fox jumps over the lazy dog 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is a famous text message because it contains all the regular characters and all the regular digits in the alphabet just one single time, no more and so no less. So this is good for some types of error checking. But so we see that we can also do stuff like encoding ASCII type of messages here. Now we're coming to the end of this extensive review, and the final question is, what is the verdict on this instrument? Is this something that you might want to have as a generic instrument in the 2020s? And I'm saying this because obviously all the type of telecom protocols that this was originally built for, they're interesting to look into, at least I find so, but they're not being really used anymore. We went to an all IP type of world in which these telecoms has become kind of yeah, old protocols. So are there generic type of uses for this instrument for which you want to have this instrument? And my overall answer to that question will be yes. If you're looking for an interesting pattern generator, an advanced sophisticated type of pattern generator, an analyzer, and you want that both in one box, one device, then I think this is definitely something you could be considering. And because there are not that many options really, both if you look at the pattern generators like pseudo-random bits and the BER analyzers that you would be using. They're rather rare and very expensive. They're not very much affordable options that would still give you enough of flexibility. The analysis is a bit of an issue as well, and to have that both in one single box is attractive. Because in most instruments they got in the lab that can do something along these lines is either a generator or a analyzer. The only exception, at least in my own lab, would be the Roden and Swart SMIQ, which has a pattern generator and which also has an analyzer, but the analyzer is optional. Actually, I don't have it myself, and I don't think it's far as flexible from the analyzer that we got over here. So having this all in one box is attractive. So my overall answer, if you're looking for advanced pattern generation and analysis, these are interesting devices. Going more into the specific pros and cons of this device, I would say, yeah, it's an advanced pattern generator with a lot of settings. You got, for example, clock recovery, even though it's an optional part of it. It's a dedicated tester that can still be used for generic purposes. And why I'm putting an exclamation mark there, I got quite a lot of other devices in my lab that all have like advanced pattern generator and even analyzers in them, but cannot be used on themselves, cannot be used outside the telecom protocol for which they are built. Actually, we're going to see a couple of them in some future videos, but the Rode CMU 200, for example, will be one example of it. Other strong points are the very good documentation, because you don't want to work with all these patterns without knowing what they really mean and what you have selected. There is a lot of I/O, including all the test bins that I've been talking about on the back. I really like the user interface. It might be a matter of taste a little bit as well, but I think it's really well thought through. It has a very high build quality. You can also see it's actually also built for on the road. There's a cover with it. I didn't show that, I think, in the video, but a cover that goes here on the front. All the buttons are retracted, so you can put it on the front without damaging anything, etc. It's a really high quality type of device. And not irrelevant, it is easy to find and well affordable still in the 2020s, because so many of these units have been built. Are there any disadvantages to the device? Well, of course there are. One of them is that if you want to use it for generic type of purposes, you probably need the LAB interface at the very least to have a direct TTL input to the device. The good news is that these LAB interfaces can be found separately on eBay and they're not terribly expensive. That's how I got mine as well. But should you not be able to find one, I think actually that if you take the serial port RS232 input on the back and the machine is just running in synchronous mode, probably it just takes a level converter, so a chip like the MAX232 or so, that would do the same trick, and I think that would create exactly that TTL input for you, although I haven't tried it because I already got the LAB interface, but I think that will be your way out basically. Another disadvantage, there is no low-level inputs, nothing lower basically than TTL. In one of my earlier videos, actually, I was facing the same problem for my Anritsu, and I built a do-it-yourself solution for that. Even though the overall user interface, I think, is really good, there are some things that could be improved, and there's some logic that I'm not totally getting. Yeah, maybe I should give some examples here. One of them would be, for example, when you're running in synchronous mode, it still offers you all the options for the settings that actually should only be valid in non-synchronous mode, like for example the length of the data words and the start bits and the stop bits and all that type of stuff. And another example would be, for example, that some of the interfaces like the LAB interface don't support the self loop mode, but still you can select it and it goes the light on as if it's activated on the front of the device. These are minor type of things, but I think they could have been improved. Not going to happen anymore for something so old as that. Another minus point I would say, yeah, there is a jitter generator and analysis, but these options are not that interesting anymore, I think, for generic type of use, because they're very limited. I mean, they're advanced, they got a lot of settings there, but they're limited to one single frequency only. So there's one complete set of boards for 1.5 megahertz for the T1 standard, and one specific board, single board in this case, for the E1 2 megahertz standard, but it hardly can be used in any other sense than that. And finally, a limitation might be that the speed of the device in terms of generating and analyzing signals is limited to 15, respectively 16 megahertz. It might be okay for your occasion, but if you really want very high rate type of bit stream for testing buses, etc., more going into eye diagram or fast buses, then you probably need other equipment, but you're probably talking about an entirely different price range as well. Now, Finally, I mentioned a couple of times that depending on what you do, you're going to need some options. So I tried to create an overview what options are relevant if you want to use this as a generic type of purpose device. And as you will see here, and I said that already repeatedly, the LAB option is probably something that you want to have. That because the TTL input and outputs. The clock recovery option is an interesting option, at least if you want to work with signals where the clock is not available to you anymore. And then there's all these other options and sets of options that you would need for the jitter generation and analysis. But like I already said, that's probably not what you buy this instrument for in a generic set. So altogether, I think this was this is a fun instrument. It's worth buying and it's worth exploring, I believe. And if you're into this type of things, then I would say consider these type of units. I hope you found this a useful video, and yeah, do give it a thumb and do take a subscription on my channel, and hope to see you on the next episode.